So, we are in the last week of our course. So, we will today start about applications of the Ito's calculus. So, you have learnt about Ito's calculus, now you should learn about applications, right. How can I do something with that Ito's calculus? One of the most important issues in finance is to express most financial processes as Ito processes. So, you wants to express financial processes, all financial processes are obviously stochastic processes as Ito processes. So, Ito processes means you have to write down everything in form of a stochastic differential equation. That is, we have seen that the Ito process can be written down in this SD shorthand as say what sort of symbol that we gave, del T dWt plus theta T dt. So, this term of a SD, the coefficient of the dt term is some in the stochastic differential equation language is called the drift term. Essentially term similar to that in finance, and this is called the volatility term, which measures the unpredictability of the whole thing. So, the first question that one arises, that can I model the movement of the prices of a stock as a Ito process? I have to model that. If I can model that, then I can bring in the power of Ito calculus to draw conclusions in finance. So, in general, you have to understand just having Brownian motion won't do. You cannot expect to model Brownian, make Brownian model as the model for your stock prices, though they may look similarly the jiggling type. But the issue here is that you have to note that the stock price always has to remain non-negative. So, that brings us to the notion of geometric Brownian motion. So, geometric Brownian motion is described as follows. Basically, the stock price at time t is the stock price at time 0, which is non-random, which is fixed, which you know because you are at time 0, e to the power. Of course, the Brownian motion captures the randomness. The question is this process ST satisfying an Ito process? Is ST an Ito process? So, we will ask this question to ourselves, is ST and Ito process? How do we go about doing anything about it, right? So, let us define an Ito process of this form xt. So, define an Ito process. So, define the Ito process. So, we are constructing an Ito process. Our aim would be to show that this is the Ito process, but let us construct the Ito process. Ito process xt, which we write as 0 to t sigma, these are constant, this sigma, alpha, these are all positive constant. Okay. This is something we need to keep in mind. So, these sigma and alpha are positive constants, these are constants. Sigma and alpha. Sigma is called the volatility, of course. So, it is sigma dWt plus alpha minus half sigma square t, sorry, dt. This is what I have. Let me define this Ito process. So, if I write down this Ito process in the SDE form, then we get d of xt So, here I have not taken x0, I have taken x0 as 0, right. So, basically I am taking, you must ask me what about the term S0, right, because in Ito process there is a term x0. So, here we are basically assuming that x0 is 0. So, then I can write this as dxt is equal to sigma dwt plus alpha minus half sigma square dt. This is the SDE form. Now, if you look at the quadratic variation of this, so the quadratic variation of the process x, so quadratic variation note that this process ST is equal to S0 like this, it is called log Brownian motion or the geometric Brownian motion. You see, because of the exponential term, this of course we are guaranteeing that a price can never be negative. So, if you want to write the shorthand form, then keeping in mind the formulas that we have given, dwt is dt, dwt dt is 0, dt dt is 0, you can then write this as sigma square dwt dwt implying that dxt is equal to sigma square dt. So, basically this Ito process has the same sort of, it is also path independent quadratic variation. So, x t is sigma square t. So, this is the quadratic variation. Now, if I look at it, how do I look at my price, right, asset price. Now, look at an asset price ST. Suppose I define the asset price, let the asset price, we have written it in this form. Actually, if you look at it, I will define the asset price as, now if I write like this, we will come to the asset price. If I write like this, what do I get? Let me write it down more carefully. I will tell you what do I get. Let me define the asset price as S0 into e to the power xt. Okay. So, S0, so you might wonder why I am writing, why I am writing in the integral form, because this is nothing but, if you look at it, this xt is actually sigma omega t plus alpha minus half sigma square t. Actually xt is this process, because if this sigma is constant, of course you can start working with sigma and alpha and s, where sigma and alpha not constant, but since they are constant I can write it like this. So, I can write this thing as exponential sigma wt minus, sorry, plus alpha minus half sigma square dt. So, though I wrote a Ito process first, just like the way I should write a Ito process, but noting that these functions are constant, I can now write from here this fact. See, integral 0 to t over dwt, integral of 1, if you just go and use the, of course, do not think that the 0 to dwt is wt just by because this is a differential, no, you have to apply the Ito's formula to come to this conclusion. Okay. So, that is the way you have written it. Now, let us see what sort of stochastic differential equation this will follow, ST will follow. So, this is the definition of an asset price. So, I want to know, I know that there is a volatility term associated with the Brownian motion and some drift term. So, we will talk about it when we explain things in finance in our next course in much more detail, but assume that this is called a drift term. And now, my question is, what sort of SDE does the, what sort of SDE does the process ST follow? Now, to do this we will have to apply Ito's calculus. Now, let us take fx is equal to S0 into e to the power x. So, we do not have the t here, x only, t is not separately taken, not ftx. So, f dash x is S0 into e to the power x, and so is f double dash x. Now, by applying Ito's formula, if I apply Ito's formula, what we will have? What we will have? We have the following. Let us see what we have. We have DST is nothing but f of x is S0 e to the power f of xt. So, it is f of xt, which by Ito's formula is f dash x dxt plus half f double dash d of xt, not d of xt, sorry, d of xt half f double dash xt dxt dxt. So, what is this? This is S0 to e to the power xt and into dxt plus half S0 into e to the power xt dxt dxt. So, let us observe the next step. This thing is your ST. So, ST into dxt plus half ST into dxt dxt. So, dxt into dxt जो है, this is sigma square dt. So, we will write again ST. Now, we will write down this whole thing. So, I am writing now dxt. So, dxt, the SD form of xt, it is sigma dwt plus alpha minus half sigma square dt. Now, here dxt dxt is sigma square dt that we have already got. So, we know that I can now replace this by sigma square dt. So, st sigma square dt cancels. So, to give you alpha into st dt plus sigma into st dwt. So, the price process of an asset. So, if you look at this is exactly the geometric Brownian motion. So, the geometric Brownian motion is following the price process of the stochastic differential equation, just like, so it is a Ito process basically, alpha st dt, the drift term plus the volatility term, sorry. So, this is the stochastic differential equation followed by a price process. So, so see the clever way we have applied the Ito calculus, we have seen this thing. So, this function, this thing we have considered as xt, the process. So, in general if you write a Ito process you have to write in terms of an integral, but we know that this is constant. So, this is, so if I do the integration, this is what I will get. So, basically this is what is xt, this is what I have taken as xt. So, then, so from here then, from here we have found that st is expressed in this form, and then by applying Ito's formula you come and show that the geometric Brownian motion actually satisfies the following stochastic differential equation, and in all the books and papers etc. you would see in finance this is the form of the stock price movement which is usually taken if you do not add things like jumps and all those things to model reality a bit more better, in the sense that there could be a sudden jump in the prices because of some problem in the market or sudden drop in the prices. So, this is one aspect. So, we go to some other application. I would expect you to work it out yourself at home when you take this as alpha t and this is, sorry, this is sigma t and this is alpha t, this is of course sigma square t. So, when they are time dependent, then what sort of thing geometric Brownian motion, what sort of a process would the price process look like? If you have a random volatility and a random drift term, what sort of thing it would look like? Okay. So, this is our first application of the Ito's calculus, which shows that our stock price actually satisfies the Ito process and satisfies this stochastic differential equation. Now, let us look at some more, one or two more applications. So, this series of lectures, the 5 lectures that we are supposed to give this week, will end with the computation of the, or rather derivation of the partial differential equation, whose solution would give us the Black-Scholes price of a European call option, which we will come very soon. But now, suppose I define an Ito integral. So, once I define an Ito integral, then what is my mean and variance? So, these ideas would be required as we do more of our studies. So, how do we recognize that what is the mean of a Ito integral? The key notion to remember is that the Ito integral IT is a martingale. Martingale means the first random variable of the process, or x0, whatever be its mean, that the same mean would be for all the other remaining random variables. Now I0 is equal to 0, because you put t equal to 0, it is 0, I0 is 0. So the expected value of I0 and we know for any t you have this and this is 0, because expected value of IT I0 is I0 because this is constant, it is 0, so it is 0. So expected value of IT of a Ito integral is 0. Now the question would be, what is the variance of the Ito integral? Now the variance of the Ito integral is nothing but expectation of I square t minus expectation of IT. But expectation of IT is 0, so basically variance of IT is equal to expectation of I square t. And this by the Ito isometry formula this is by the Ito isometry formula. Now these ideas would be helpful as we do our next applications. We will talk about how to model interest rates in the next class. So we will just introduce to you what are interest rates. We will not get into tremendous amount of details about finance, because there is a lot of issues when we discuss even very basic concepts of finance. So what is an interest rate? Suppose I have 1 rupee, I invest in a bank and the bank tells me that after time t you are going to, after time small t you are going to get back or some money with an interest rate r, which means he is going to pay me after time t not only rupees 1, but the interest rate, which is the percentage, rupees r into 1. So not only the principal, but the fraction of my principal would be added to my original money. So this is what I will get, 1 plus r. So after given period I will get 1 plus r money. So this r, this fraction is called the rate of interest. Usually what happens is that bank, suppose you have kept money in a bank in a fixed deposit, or you have taken a loan, so you are paying back money to the bank. So usually for a given period, say between time small t to capital T, for a very small period the bank interest rates are usually kept fixed. This is called a risk free rate of interest. This rate of interest, it is called risk free, because I guarantee you that if you take money from me now, after say 1 month, I will give you 1 plus, if you give me 1 rupee, I will give you 1 plus r rupee. So that's what's, for example, if I say if you give me 100 rupees now, I will give you back after say 1 month 110 rupees. So, my interest rate is 1 by 10th. So, R is 1 by 10th. So, that is sort of idea. So, the interest rate usually in a bank is kept at a hold between, and it is held for very short time. Usually, the interest rate keeps on changing in the bank. So, in general, people, just like in physics, we want to know what is the instantaneous velocity. It is very difficult a concept. It is not so easy to understand, and we do a lot of problems and do a lot of things with it, but instantaneous velocity is one of the most deepest concepts. It is not so easy to fathom it immediately. Similarly, we will talk about instantaneous interest rates. What is the interest rate exactly at time t? So, just like we did in physics, that we look at the difference of the distance travelled by difference of the time taken and take the ratio and then take the limit as the time goes towards 0, and that is what we call instantaneous velocity in mechanics, in physics. Similarly, we call or rather I should say that is called the instantaneous rate of velocity at the time, sorry, instantaneous rate of interest at the time capital T. So, here RT or in general RT is the instantaneous rate of interest or sometimes called short term interest, instantaneous rate of interest. So, but this rate of interest is random, it changes, this itself is random. You cannot say that today the interest rate is this, next day the interest rate will be as per as you have decided, it will be just based on the market, it will change. So, RT is called the instantaneous rate of interest. Our next question would be, can this RT, this instantaneous rate of interest, which is now essentially a stochastic process, it is a stochastic process, we are asking the question, is RT an Ito process? Is RT an Ito process? So, with this we end our first lecture of the last week, and in the next class we are going to answer whether RT is an Ito process or not, and what sort of models have been there for RT and how Ito's calculus help us to understand those models.